Hello everyone. In this video, I will use dynamic analysis to simulate the damping behavior of the suspension. Here, initially I will apply a load, compress the spring, then with the spring's own inertia, it will move. Let's see. In the previous analysis, I calculated how much load is needed to compress the spring by 4 centimeters. This is the run, took only 4 minutes, check the phase calculation and reaction force, and I ramp up my displacement, and finally around 468,000 newtons. It reached. That means this is the force value required to compress the spring by 4 centimeters. The nodal results should be in opposite direction ideally and the same value. Yeah. Let's switch to our dynamic analysis now. My CAD model, create simulation, and use a dynamic one. The nice thing here is that I have the identical model. Since this model is already meshed, I don't need to remesh it for the new analysis type. Here again, 2 contacts are identified, but in the previous video I said they are not correct. You need to modify that. I will skip this part of the video since I've done that in the previous video. I edited the contacts, but as I said, you can switch the physical contacts here for better accuracy. Now, what else can I do? Under model now, I need to define the direction of the gravity. Let's say this is my gravity, and the direction is minus z. And material, again, I will use linear default steel material on every component. And I don't have any initial condition. How about boundary conditions? I want a fixed support, again, exactly on the same location. And I want to apply load this time. Since from the previous simulation, I know how much the load should be. It was around 460,000. Let's adjust the time. This is not arbitrary time anymore. This is a real time. At time 0, my loads are 0, but starting by the time 0, I will increase my load. In such a short time, I will increase my load to maximum. Then, soon after, I will stop loading the system. And until the end of simulation, I am not expecting to increase any load. I want to simulate this for 0.2 seconds. Now, I have a load here, but I did not define any constraint. The solver does only know that it should add a load with respect to negative z direction. Let me check. Yeah, okay, this is negative z direction. I need to tell the solver that this piston is not going to rotate axis. However, I'm unconstraining the z direction, so the piston can freely move along the z direction, z axis. Now I want to define the time step of this simulation. This simulation will end in 0.2 seconds. The time step length, I want to adjust this manually, because until 0.01, this simulation, I'm loading the system. So I want smaller time steps here. And after the unloading, the spring will bounce. So until 0.05 seconds, I want some fine time steps, 0.001 seconds of time step. Afterwards, until 0.2, I want some larger time steps to preserve the computational hours. All right. Now I can again add some result control items. I will again add a reaction force on my fixed support displacement. Select the fixed support phase. And now I will also add an average displacement results. Around here perhaps, or if you want here too. Average displacements, yeah. Because I want to see how much displacement simulation has finished. First thing you can check is the phase calculation reaction force. As you can see in the beginning, we just loaded the system, then removed the load, but then afterwards we still observe some reaction force. That's because of the spring bouncing. Checking the displacement, we should see a similar behavior. Yeah. Initially, with increasing loading, 4 centimeters displacement achieved. Then we removed loading, so it came back to 0, but then to the other direction because of the bouncing. So it's keep bouncing between negative and positive z-axis. Let's quickly see the result in post-processing. Okay, this is end of the time. You can press play button to see this animation. So this is what happens. Initially compression, then leaving the system to its own inertia. You can switch to different units, and by adjusting this bar or typing some maximum and minimum values, you can adjust the bar too. Alternatively, you can plot different result types such as acceleration, velocity, or stress.